So I will talk about Eggman type flows. So basically, so the wind-driven currents and motivation a little bit, they are very important to regulate extremes of temperature because roughly 70% of the Earth's surface is the ocean. And then the upper 3 meters of the ocean stores as much heat as the entire overlying atmosphere. And also for greenhouse gases, and it's the upper part of the ocean that plays a very important role. There are also deep currents because of differences in salinity. They also play a role, but the most important processes of heat transport are at the surface, and surface currents are basically driven by wind. This is the basic system that I will look at. So F is here. It's the F-plane approximation. U is the horizontal. U and V is the horizontal. Are the horizontal components of the velocity. Z is the vertical variable, and K is a depth-dependent vertical eddy viscosity. The boundary conditions that are associated with this system are, well, at the surface that I will take to be at Z equals 0, what you have is the wind stress vector is related to the shear stress in this way. Rho is the constant density. And so I have this condition at the top, and then there's the other condition that deep down the effect is negligible, which is deep down, so U and V and the Z derivatives both go to 0 as you go at great depths. I mean, below a few hundred meters, this, in practical terms, this will not be, the wind will not have an effect, but I will take this form. So this is the basic system I'm looking at, and there is a famous and classical solution by Eggman in 1905, prompted by observations of Nansen. So what Eggman did, it's this system, and you take constant eddy viscosity. And if you take constant eddy viscosity, then you can solve it explicitly, and that's the formula here, written out in complex variables. And, okay, lambda is this constant here, and in this formula comprises the most, I mean, you can read off the formula the important features. One is when you set Z equals 0, so you are at the surface, this is 1, this is gone, and this is a rotation. So what it means is that at the surface, you know that the surface current, you can see how, well, what its relation to the wind stress, but most importantly, you can see that there is a deflection of pi over 4 that is there. This is in the northern hemisphere, okay? Because I take F positive. In the southern, the direction is changed with respect to the wind. So what you see first, so it is, the surface current is deflected by pi over 4, by 45 degrees. You see that the current decays exponentially with depth, and what one can do is, it rotates, so it's because of this. So it's a spiral that I have a standard. So the surface current is at 4, this is the wind direction, it's a steady wind. The surface current is at 45 degrees. Then, because of the e to the I, it will decay and rotate in this direction. And in addition, what you can also do, you can take an average of the mass transport. And what you can see, well, you can compute this explicitly, it's just this. So what it means is that always the mass transport is at 90 degrees to the wind direction. All this is in the northern hemisphere. In the southern, it's rotated. And this is not valid at the equator, because at the equator, what you will have is this theta is 0, so you don't have this balance. At the equator, it's more complicated. Actually, nonlinear effects play a role, so I will not discuss the equator. I will concentrate on the northern hemisphere, and my goal would be to try to understand what is happening with this system in the general case when K is depth dependent. So some general statements that one can show what is going on when K is Z dependent. Now, this problem, of course, is a classical problem. It's motivated by the fact that there are field studies where data that is field data confirms these predictions by Eggman. So there are, for example, the Eggman's classical solution fits well with the wind-driven currents in the Southern Ocean, the one around Antarctica, and in some coastal straits. So there is matching between Eggman classical solution and field data, but there are also places where there are changes. So, for example, the most visible one is this 45-degree is deflection at the surface. It's typically lower, as low as, well, it could get below 20, but sometimes you also have values in excess of 50 degrees. So it changes. And one thing that has also been noticed is that the deviation from the wind is typically larger during the day than during the night. This is also the case. So now there are two ways you can address this, and one way that we have experts here in the audience. The Eggman solution is not just for the ocean, you have something in the atmosphere also. So what you can do, and it's very helpful to try to find specific eddy viscosities K, for which you can either find an explicit solution. It won't be as elegant as Eggman's, but I mean, if K depends linearly with Z, then you can do something with Bessel functions. There are very few, explicit solutions where you can find a formula for the wind drift current, and there are some results where you can get a good approximation. So even if you don't find an explicit formula, you can find a reasonable approximation. Now, it's really for a general K, so in general, the kind of eddy viscosities that are encountered, they are not necessarily, they are not constant, they are not necessarily monotonic, so you can have, sometimes they could be increase or decrease with depth, but you have also profiles with multiple local extrema. In general, however, the non-constant eddy viscosity explicit solutions there are relatively few of them. So what I'm going to talk about is what can you do in general. And so the aim, what I will show is that, first of all, the first thing is it follows directly from the equations, that this 90-degree transport is always valid. That's an easy calculation. The other thing is you always have this spiral in the sense that the current decreases, the horizontal current decreases with depth, and it will continue to rotate in the same direction as the one that you see at the surface. So there is a spiral. And the third aspect, I consider a perturbation. So I consider an eddy viscosity constant plus a perturbation. Okay? And then I will show that there is, whether the deflection angle at the surface is larger or smaller than 45 degrees is decided by whether this integral here is positive or negative. This is in the northern hemisphere. and then I will discuss a little bit what this tells us. So this is a weighted, this is the non-constant. If you put in, if K1 is constant, this is 0, as it should be. So when it's a constant, you don't see anything, but when this is not constant, this integral will decide whether the deflection angle is less or larger than 45. And and it's an integral. I take this perturbation here to be positive, so this will change sign plus and minus, because this expression here changes as z goes from z equals 0 towards minus infinity. Okay, so this is the aim. Now, the methods, the first property, so the 90-degree mass transport, the Eggman transport, is simply by integrating you write the differential equation in complex form, you integrate, it comes elegantly out, and you get this in general. And this is the 90-degree that always holds. For the second property, so that the wind drift current is a spiral that decreases and rotates, I will adapt an approach that we developed with Robin Johnson in a recent paper about the atmospheric flow. So I will adapt this to the ocean context. And for the formula, what I will do, I will adapt and simplify an approach developed with Bressan, so what I will going to present is simpler, because with Bressan what we did is we took this equation here, so the governing one, this one here, no, not this is the boundary condition, this here, and okay, this is a weight here, so what we did, you have a Liouville transformation and then transform it into a standard form. The problem is you get the formula, but that formula will be, because you perform this Liouville transformation, this is the Liouville transformation that you have to perform, K0 is that constant, all the formula that you get for the deflection is expressed in terms of this new variable, and that's not the real depth, but so it's more complicated to interpret this, and it would be better to have something in terms of the z, the physical z variable, and not some implicit variable like this. So this is the plan. So the first property is done with. Now, for the second, this is the spiraling property. It's an interesting thing that, okay, what you do, because you want a spiral, if you remember, well, if you look at standard courses on differential geometry for curves and surfaces, it's easier to write spirals in polar coordinates, because then you know what the radius will do and also what the angle. So one might try this here. So this is the flow speed, m, and the angle such that, so I write the horizontal wind drift current in this way, and then the system with the k transforms. I mean, you can play around and compute the second derivatives, multiply. It gets transformed into this system. This is a nonlinear system. Okay, so m is the speed, theta is the angle, and this is a second order system that is nonlinear. And it is equivalent to the original system where m is positive. M is the speed, so I'm going to show actually that m, if m is different from 0 at the surface, it will always be strictly positive, so this is actually equivalent to the original system. At first sight, it looks like a complication because now we have a nonlinear system, but this system, you can read off interesting properties from the structure of this system. So what I want to show for this system is first that if m is different from 0 at the surface, so if you have a deflection, then it will continue to be positive until, and it's going to decay. So, and then what I want to show is that the angle theta, so theta of 0 has some value. I'm going to fix it I'm going to discuss the northern hemisphere, and then I'm going to show that this theta, basically theta prime, has always a sign. So that means it can, so the spiral is only in one direction. And what that sign is depends on the sign of F, so that depends, which is decided by whether you are in the northern or southern hemisphere. So this is the nonlinear system. All right, the boundary conditions, just to express them in terms of M and this theta, this is, so you can introduce a beta, so you can write the wind stress also in polar coordinates, and then these are the boundary conditions. And, well, beta is the direction of the wind at the surface, alpha is the strength of the wind stress. And now, field data typically shows that this is how the wind stress at the surface is related to the wind speed. Typically, this is taken at 10 meters above the sea surface. Okay, so this is the wind stress, the relation between the wind stress and the actual wind at 10 meters, but the important thing is these are the boundary conditions plus the decay. So, if you look at Eggman's classical solution for constant eddy viscosity, and you wonder what does it correspond for this nonlinear system for polar coordinates, this is the solution, where the values of these constants are here. So, again, this is the speed, it decays exponentially, and this is the angle, and you can see here the angle, depending on the sign of F, lambda is always positive, depending on the sign of F, the rotation is either in clockwise or counterclockwise, depends on what hemisphere you're in. Right, so now this is an explicit solution. For a general depth-dependent eddy viscosity, what you do, the first equation in this polar system, you can read it off and see that it's this. Now this is positive, so this is an increasing quantity, right? And it decays down, so there it's 0, it's positive, so M prime has to be positive. This gives you so the polar coordinates gives you automatically the fact that M decreases as you increase the depth. And now I want to show that it's always strictly positive, because if there would be a value where it's 0, because it's always positive, then below this Z0, it will always be 0. This is the monotonicity. And because it is 0, then at this Z0, if you come from below, you will have M and M prime 0. And now you go back to the system in polar coordinates, and you interpret this equation as a second order ODE in M. It has smooth coefficients, and this is the initial data, 0, 0. There can only be one solution, and that's 0. So if it's 0 somewhere, it has to be 0 everywhere, and that's not possible. Therefore, it is positive all the time. This already shows that it is useful to work in polar coordinates. So what this tells you is that it will decay as you go down. And now what I want to do is I want to look at, to show that the rotation is always in one direction. So that means what I want to show is that okay, I look at if you look at the second equation, there are coupled equations so I'm talking about this system here, yeah? And this is second derivative in M. This, if you look at it, is second derivative in theta, and they are coupled, M and theta and derivatives, and it's nonlinear. But this one here, so in the first, to deduce that M is decreasing, I use this equation. Now, for the properties of theta, I'm going to use the second one, describing the time change, the change in, it's not the time, the change with depth in theta. So what I want to show is that this is always positive. I'm in the northern hemisphere. So I want to show that this is always positive, so the spiraling is always in one direction and it never stops. Assume there is a point where this is less or equal 0. Then, again, this thing here, you read it from the equation, this is monotone, and you deduce that below this level, it will have a sign. It will be strictly negative. Now I denote this I fix something below this level, it doesn't matter what it is, and then I know that this is strictly negative. Yeah, this might be 0, so this is why I have to go a little bit below. And then, because of monotonicity, I have this. Now, You go back in the first equation, this is this, you write it like that. With an inequality, you get this bound here. So this is greater or equal than that. And now you multiply both sides with this, and you get this expression, which when you integrate, you find out this differential inequality. Now, what does this tell you? This should be valid below that Z star level. And if you read this off now, this is a contradiction. Why? Because this will go to 0. This is the decay. So what this means is this is at great depths, at Z going to minus infinity. This is gone, and I'm left with this expression that is a negative number, but it's a fixed. I mean, it's a finite number, negative. On the other hand, if you look here, the right side will blow up because of this. The right side will blow up, and the left side okay, sorry. This is, yeah, this is finite and this blows up. So this is infinity and this is finite, so you cannot have it. So this shows that you always have this, the rotation is, it's a spiral that keeps on going and it decreases. And now I want to look at this proof for the formula for the deflection angle. And just like in the calculation to derive this classical Eggman solution, you introduce complex variables, so introduce this complex function, and you write the governing equations in this form. So this is, you see, this is like it's a second order ODE, but with a weight here. And it's for Z less than 0, and the boundary conditions can be expressed in this way if you work them out. So now this is, so what I want to do, I want to use a perturbative argument, so I write the solution as the Eggman solution, corresponding to the constant viscosity K0 plus the perturbation. And you put in the epsilon, you make the calculation. This is the second order ODE satisfied by psi 1, okay? And if you work it out, what you get for the northern hemisphere, it's this. This is the classical Eggman solution, so when you can plug it in before, and what you find out is that this is the ODE for the perturbation. So this is a constant, which is good, but all the fact that the eddy viscosity depends on depth is hidden in this forcing here that takes on this form. K1 is the non-constant part, leading part in the eddy viscosity, and these are K0 is the constant part, and F is this Coriolis thing. So, and psi 0 is Eggman's solution. So basically, if this is gone for Eggman, but you have a forcing here. And the condition, I mean, for the perturbations, the boundary conditions are just the derivative should be 0 at 0, and there should be decay. Now, I don't have here the derivative for, so it's just one initial data and one asymptotic condition, because, I mean, normally I should also have psi prime go to 0, which was part of this, but that follows at once if these two are true, because, oops, sorry. Right. Because, okay, so this thing here is the missing condition that I just ignored, and I can ignore it, so the claim is that if psi goes to 0, then because of the and I have a solution, because of the ODE, the second derivative will also go to 0. And now when you have a function and its second derivative going to 0 at z going to minus infinity, then the first derivative will also have to go to 0, which is this missing condition that I can neglect because of this. And this is because there is a nice inequality here that you can use you can prove using Taylor expansions, namely, if m0 is the supremum of the function, m1 is the supremum of the absolute value of the derivative, and m2 the supremum of the second derivative, then you have this squared is less than this. And what this means is that if both of them go to 0, then this has to go to 0. Actually, this inequality is much stronger than that, but I know that both of these goes to 0. So that means that this is redundant, okay? And explains why, for the perturbation, I have this linear ODE with this initial condition and that boundary. So the derivative should be 0, and the solution should go to 0 at great depths. Okay? And now, so the ODE is constant coefficient and with the forcing that depends on Z. And because it's constant coefficient, I can write it as, well, in the standard way as a first order system, and then I have the variation of constant formula where this is the fundamental matrix. And the fundamental matrix, because it's constant coefficient, you can compute it and it has this form. Okay? So what it means is that the general solution will be this. And what I will do now is I will say, okay, I know that the initial data, I mean the data that I have is that the derivative should be 0 at z equals 0, and it should go to 0 as z goes to minus infinity. So I'm going to use this information to simplify things, namely for the following way. Okay, first of all, psi, this is the part in the solution that is different from Eggman. So it's this. We get that the solution that I'm looking for has this form. And, okay, this is the initial data, and I will have to specify this to ensure this asymptotic one. Okay? So because psi 1 prime is 0, the solution has to be this, where this constant here has to be chosen to make sure that you have this asymptotic condition satisfied. Now, when you look at these terms, this one here, this one is okay, this one will decay, so this has no contribution, this doesn't tell you anything. When you look at this expression, well, this is part of the integral, so I'm claiming this doesn't matter and this doesn't matter, so you're left just with this and that. This thing here, this limit is 0 because, well, dominated convergence, you can bound things and see that this will go to 0. So basically, if I write this in this form, what I can see immediately is that this part here will go to 0 at z equal minus infinity. This one will go to 0, so it's this part here that I have to make sure that it goes to 0. And so the asymptotic condition, because this blows up, has that psi 1 has to match this as you go to minus infinity. So this is a necessary condition to make sure that psi 1 goes to 0, this one here. And if this holds, then I know exactly what psi 1 of 0 is. It turns out that this condition is not only necessary, it's also sufficient, that you can see using L'Hopital's rule, okay, this. So what it means is that if you look at the perturbation, then this is psi of 0. Okay? This is the explicit formula for psi, and, well, this is the derivative. And because I have a derivative here, I can do some integration by parts and write psi of 0 in this nicer form where there are no derivatives. Okay? And now I can use this, and I can compute the deflection angle. It's some constant times this, and this is where this integral comes in. So basically, this is the proof that for the formula, this tells you when this is positive or negative. When it's positive, it will be bigger than pi over 4. When it's negative, it's going to be less than pi over 4. This is the proof. And what I'm going to do next is to try to analyze what this tells you. And the important thing is K1 is something positive and bounded. This is something that decays, but this function here changes sign. And because it changes sign, it's kind of complicated. So the vertical structure of K1 will definitely play a role. I mean, will determine whether this is positive or negative, but I can one can, by looking closer at this formula, one can understand how this is going to come about. So what you can do, this is the function that is integrated. So this integral, positive or negative, decides whether the angle is less or more than pi over 4. And what you can look, because this is a sign, this has a sign, you look at where this changes sign. So first, it's positive in an interval that goes z equals 0 is the surface until pi over 8 lambda. Now, there is something that I should, well, right? So until something of length pi over 8 lambda, this is a small interval where it is positive, then it becomes negative, so it alternates, it's a sign, so it oscillates, it alternates sign, but these intervals here have length, if you look at them, their length is pi over, it's the double of this, it's pi over 4 lambda, okay? So you have a small interval, and then intervals of double size where alternatively it's plus, minus, plus, minus, plus, minus. So I can compute, so this is what these intervals were the intervals where this oscillating function changes sign, and now because it's easy to integrate this, to compute these integrals, I am computing the integral without the k1. Yeah? So just the integral, and these are the respective values. Okay? So I'm going to think that I'm going to approximate k1 with the constant in each of these intervals to understand how the contribution from all these intervals matters. But what I need to do is this weighted integral, so not just the sign, but also with the exponential. So these are the numbers that you really obtain, and I will denote by EM the absolute values of these integrals, because the first one is positive, then negative, then positive, then negative. And these values are monotone, but not starting with the first one, but starting with this one. Yeah? So there is a problem between the first, E0 is less than E1, but then it starts to be monotone. So the biggest one is the second one where it's negative. And then they decrease. And this has, right, so now you can take k1 to be constant on these intervals, and this will tell you that the key to whether this integral is positive or negative is basically decided, this decays exponentially, so at great depths it won't matter. The contribution will be very small, but it matters the relative sizes of E0 and I0 and I1, this is the first one and the second one, that's what is deciding. I0 is, in I0 this is positive and then it's negative, okay? So, what is pi over lambda? So I0 is pi over 8 lambda, and then, so the first one is pi over 8 lambda, and then it's pi over 4 lambda. Pi over lambda, in Eggman's classical solution, is the so-called Eggman depth, where it's for the, so this is a spiral that rotates, and the Eggman depth is the depth at which the wind-induced current for the first time points opposite to the wind, opposite to the surface. Yeah, so you have the surface current, and this is the first depth, it's a spiral. So this is pi over lambda. So basically, if you think in terms of this Eggman depth for the constant solution of this, of which K1 is a perturbation, then in the upper eighth part, you have something positive, then 1/4 of the length is negative, and then they alternate. So this is the upper eighth part, then this goes almost to the upper half, but it's 3/8, it's not actually 1/2. So a slow and gradual variation of the eddy viscosity will result in a positive integral, because the one at the top, because these things vary but not much. But, okay, if the eddy and the deflection, and then the integral is positive and the deflection angle is bigger than 45. If the eddy viscosity in I0, this is the first level, is lower, then the negative contribution, it's bigger, it's twice as big, will dominate the positive and the rest will not matter, and you will get an angle that is below 45. Okay, this is the mathematical analysis, but you can read now in terms of physical consequences. So in Arctic regions, what you have ice, typically, or some ice, and that quells the turbulence. So what it means is that near the surface, this will be smaller, typically, and so the relative sizes of the contributions from I0 and I1 will be such that the angle will be less than 45 in Arctic regions. It also explains why the deviation from the wind is typically larger during day than night. Because typically solar heating, I mean, I have data for this, so solar heating, turbulence is lower because of solar heating, and all these changes happen in the upper part, in the upper 100, 200 meters. So the contribution from I1 is amplified, and typically this leads to an overall negative integral during nighttime. Okay? So indirectly, I'm not putting time in the problem, but I look at the effect of time in changing the eddy viscosity. And this also explains why there are seasonal variations in the deflection angle. Among the most spectacular ones are in this strait near Japan, where during winter you have this kind of deflection angle, and in summertime you have this up to 67 degrees deflection angle. And it's the same story because of the relative sizes of I0 and I1. I mean, this perturbation, even if the eddy viscosity is non-constant in general, I will take that it's a slow variation, so it's not something drastic. So this is what I had to say. Well, you just have to, so B is the, so what you do, oh, sorry, here, okay. So what you do, you write K as epsilon psi, and then you get this equation. And now what you do, you use psi 0 is Eggman's classical solution. So when you put that in and you compute, you see that the leading term, the second derivative is with the constant. The first derivative is with the second derivative. Psi 1 has just a constant coefficient, and this is where the B comes from. So it comes from the classical Eggman. It's just by computation. You have to compute and to reorganize things. So I just put in here, rather than, you see, this is Eggman's solution, and this comes from second derivative and first derivative of the Eggman solution. So there are these two terms here. It's this one. This is the first derivative of the Eggman solution. This is the second derivative. But when I wrote B, I just wrote psi 0. This is Eggman's solution, and I computed what these coefficients are. So it's just a computation, an explicit computation.
Yes?
Yeah?
I think it's a technical comment. But since your nonlinear system
Yes.
is an exact form or different but exactly identical form to the linear one, I think you could easily argue that all the results in the linear system that are independent of K should hold in your nonlinear system as well, which I think might save you a lot of the headache that you went through hoops trying to prove some of the intricacies of your nonlinear system.
Yes, but I don't know how to prove these things on the linear system.
No, not all of them, but I'm saying there were elements in it that if it's all the results that are independent on K,
Yeah.
the linear system should hold just as well in the nonlinear system.
Yes.
So your monotonicity, for example,
Yeah, but I mean, I can prove monotonicity and that the angle goes like this with the nonlinear system, but I don't see it in the linear system. I mean, maybe it's just me. Well, I showed it for the nonlinear system, and therefore it's valid for the linear system. All these manipulations that I did with the m derivative of m and theta are for the nonlinear system.
Right. But also when you started out,
Yeah.
you had results that were, some of them were independent of k, but later on became k.
Yes, yeah. It's just a deflection formula.
All of them should hold just as well in the nonlinear system.
Yes, yeah, I agree.
I think if you just employ some of them, you could have probably circumvented some of the...
Maybe I tried to simplify this. I mean, obviously it's not the first time, because in the atmospheric case we did something along these lines, and I didn't find a way to make this simpler, but that doesn't mean that there isn't one.
So, viewing it as a little differently, if you just take now and divide the Eggman layer into two sublayers,
Yes.
and just in each one of them solve the linear system and just match it at the interface,
Yes.
will you get different results?
No. It's the same thing.
So
It doesn't matter.
Then your qualitative conclusions could be derived by just doing two linear systems and matching them instead of the nonlinear.
No, because I don't, the only way I can prove it is using the nonlinear system. So it doesn't matter what I know, I mean, all these conclusions, the one about the qualitative behavior that is a spiral, I can only prove them using the nonlinear formulation. And it doesn't matter what the k does. It's because the k is at lower order, so it could have discontinuities. It doesn't matter. I integrate it. We are not talking about weak solutions or shocks or things like this. Everything goes through. But although the system is nonlinear, somehow for general k, the structure is visible there in an easier way than in the linear system. And my explanation for this is when you look at all these studies, well, at most studies on spirals, I mean logarithmic spirals or whatever, it's always useful to use something like polar coordinates. If you try to work without polar coordinates, you won't see a lot of things. And this is some...
Polar coordinates have been used also in the linearized system. I think Gill does it in his book.
Well, I'm not saying, of course, I mean, it's a basic change a first-year student can do. The thing is that the system has then the structure that you can exploit. That's what I'm saying.
Just a comment. I mean, the original system in terms of U and V is already linear, so you've made it nonlinear by doing a polar coordinate transformation.
Yeah, but
that's just a comment.
Yeah, it's just, I mean, I'm actually working. I mean, I made a change of variable, and it's not just because I like nonlinear things. It's because this works. I mean, I tried something else. I mean, I think there must be a linear proof, but I don't see how. I don't see how to prove this without using this ugly-looking system. Well, because it is actually ugly.
The work we did that Adrian referred to, we could find no way of getting a handle on the detail using the linear system, which is a real surprise.
Why? If you take two layers with different k's.
Yes, that constant K you're talking about.
Yes.
Yeah, but then you can compute explicitly.
If you match them at the interface,
Of course you would do that.
Yeah, but that is something that you can do explicitly.
But
This is not, I mean, this is in general.
But I think what Nathan's saying is that you could actually chop up your interval into small intervals and take the limit of an infinite number of them.
It's true, but you know, you have to chop it. If you look at this formula and the intervals with I0 and I1, you have to chop it 1/8, 1/4, and then 4th. So how would you know this when you start? Why is it 1/8? I don't see why, but
I do have a question.
yeah.
You dismissed the equator neatly because it's nonlinear. Can you make any comments about that?
No, well, this system is not valid at the equators. It's more complicated. I didn't look at it. I mean, this is just.
it depends on who you ask.
Yeah.
If you ask a descriptive physical oceanographer, they will just say there was wind with no Eggman, so it pushes the water westward. And that's what you read in all the descriptive physical oceanography textbooks, which is all wrong, because they confuse force with velocity. Or
So at the equator, this system is not valid. One would have to work with something else.
Stomach's gyrus, or Mach's gyrus. To understand what's happening on the equator, this is way beyond this unified field. 3D problems.
Yeah.
So just a quick question. I was following your existence and uniqueness argument for the second order ODE, that
Yeah.
is equation 5, right? You were saying the coefficients are smooth, but as you know, you also need the leading order coefficient to be non-zero. Because, right, you would be right to be non-zero, because it's...
It is. The leading order coefficient is the eddy viscosity, so that's positive.
But it cannot vanish at some point. One cannot say that because K as a general case.
Well, I take it, I think, so I took it to be positive everywhere, but I think that's not, it's not a problem. I mean, even if it just becomes a little bit more complicated. But if you take it positive, then there is no problem because this is, I mean, it's really the standard existence and uniqueness. If it has zeros, this goes through, but then it becomes technically more complicated. No, but then what you do, you see, if you have a zero, then it should be zero below that because you decide, okay, eddy viscosity doesn't matter. And then all what I did here, instead of going to minus infinity, I do it from that level up, and it will work through.
It would not make sense physically for that Z is the depth, right? That
Yeah.
Some depth it's 0 near 0 and then goes back to non-zero. So that would not be feasible.
No, I mean, I think it will work, but I did not. I mean, this is quite recent work. I mean, it's something that we did with the atmospheric counterpart of the spiraling we did last year, and this is something in the last. So I did not explore all these possibilities. I just wanted to look at the, so to say, the most basic case and to see what one can get there.
Hopefully a very final small comment about eddy viscosity. Of course, it's been known since famous experiments going back probably to the 50s and 60s that you get density layering.
Yes.
And of course, that led to Victor Starr's concept of negative viscosity, which of course is the wrong way of thinking about it.
Mm-hmm.
But it does question the idea that there is an eddy viscosity formulation of the type that's being assumed in the Eggman spiral. In particular, such a diffusive model can't explain the density layering effect that results from turbulent mixing, which is well known to happen both in potential vorticity and horizontal mixing, but also in the vertical mixing problem in density stratification.
No, but I think it's, well, so here I take constant density. If you take the density to vary with depth, then it's not the system you have to, and there are some systems, I think there is this group in Seattle that does this kind of things where they derived not the Eggman thing, but something that looks superficially like the Eggman thing for density variation. So these are people like Kessler and Cronin, and so they did. So there is a system that looks like this one, but it's, I mean, superficially it has the same structure, but like I said, I mean, I would like to look at this, but I started with the most basic one. I think that something should work through with that, but of course, the devil is in the details, I don't know. But that is an important issue, especially at the equator, where this anyhow doesn't apply. But they have something that looks like this with the forcing also at the equator. So there are the issues of density stratification, and then of course it's the time-dependent problem that is more difficult, but that's another story.
Density in your equation?
Density is constant for me.
Right, but where is it in 5?
Well, in the, somewhere in, it's in, you see, it's, well, it's there for.
The original, I know where it is, but in 5, in your nonlinear system,
What is 5?
where is it high?
Well, it's constant, so you won't see it. You won't see it here. It's just. Well, it's in the scale of, I mean, when you look at M, you see the easiest way to see this, if you look at, right, this is, this, it's here, yes, you can see it here. So this is Eggman's classical solution written in polar, and it's a coefficient of M. It's something that multiplies the speed.